Hi, welcome back. My name is James McConnell, and in this video, we're going to continue the series of discussing some interesting patents. This patent today is going to be the capacitive discharge electromagnetic propulsion system, and that's been filed by the inventor James Wayne Purvis. So without further ado, let's jump into this. We're going to be looking at this segmented current magnetic field propulsion system from the inventor James Wayne Purvis, once again, and want to focus on the figures today and the description of the figures. This was published in 2019, filed and published in 2019. Okay, so firstly, let's actually scroll to the claim. What is claimed? What is claimed is an electromagnetic field propulsion system comprising a structural support plate having a plane form shape of a circle, oval, triangle, or other end-sided polygon, and comprised of any combination of lightweight non-magnetic material selected from the group consisting of aluminum, titanium, high-impact plastic, fiberglass, and carbon fiber composites for the purpose of maintaining specific component geometries. So we need a certain frame for this device that's not going to be responding to any sort of magnetism. We need a conducting coil comprising one or more turns of insulated conductive wire wound in a manner of an air core solenoid. We need a plurality of magnetic field shield assemblies for the function of attenuating magnetic fields directed onto designated shielded segments of said conducting coil. We need a reaction thrust assembly comprising the structural support plate, the conducting coil, and the plurality of magnetic field shield assemblies, wherein said plurality of shield assemblies enclose segments of the coils, and wherein both said conducting coil and said field shield assemblies are attached circumferentially to the structural support plate. At least two field activation coils comprising insulated electric current conductors wound in a manner of electromagnetic solenoids on cores having relative magnetic permeability of at least 2 for the function of generating directed magnetic fields onto unshielded segments of the conducting coil. We need an energy supply unit attached to the structural support plate for the purpose of supplying electric current for these at least 2 activation coils. And we also need to supply power to the conducting coil of the reaction thrust assembly. This energy supply would be comprised of any combination selected from the group consisting of storage batteries, fuel cells, solar panels. So pretty much any energy supply is sufficient. And finally, whereby if we do all of this properly, a net unidirectional Lorentz force acts on the electromagnetic field propulsion system, wherein this net unidirectional Lorentz force results from electric currents in the at least 2 field activation coils generating the directed magnetic fields which interact with the electric current in the conducting coil of the reaction thrust assembly. Further, wherein reaction momentum is carried away by Poynting vector fields, thereby producing thrust on the electromagnetic field propulsion system without expelling propellant. So what are we doing is we're setting up a unique configuration of coils and magnetic shielding components, running current through that, and it seems to be producing a net unidirectional Lorentz force that's actually able to move this device. Okay, so let's go down to the breakdown of each of the drawings. All right, so let's go through these figures now. So we've got figure 1, which is a schematic illustrating the unidirectional Lorentz force acting on charged particles moving orthogonally in the same plane. So these seem to be the charged particles moving orthogonally. I think 2 might be that Lorentz force. I'm not sure if that's the case. Get a T in there. Figure 2, schematic illustrating the unidirectional Lorentz force on a segmented conductor due to perpendicular electromagnetic coil. Okay, so we have, once again, we're seeing these arrows illustrating the force. We have the electromagnetic current as well, or the electric current. So I think 5 is the wire. I'm not entirely sure of that. And then I'm curious to see if we can get an understanding of what this rectangle this polygon is. Okay, let's go to 3A and 3B now. We'll pull in 3A and 3B. For figure 3A, this is illustrating magnetic field lines about an isolated magnet and about a magnet in the vicinity of an iron plate shield. Okay, so this is pretty standard, just showcasing the ways that magnetic fields behave based on certain parameters. So standard behavior. And then if we introduce this iron plate, we can see how the wave changes, right? Figure 4, schematic illustrating magnetic field lines about a Misner effects semiconductor above and below critical temperature. So I think this would be above, maybe below. So in the case of above, if this is correct, then the magnetic field lines don't curve at all. Whereas in the case of figure 4B, they're completely curving around this, whatever this here is in the center. Let's go to figure 5. All right, that looks like an eyeball, but I'm sure it's not. In a schematic, this is a schematic illustrating radial magnetic field induced on a planar circular conductor by a coplanar electromagnetic coil. Okay, so once we get into the detailed description, we're going to look at what these numbers are. Just kind of pull this up for now. Let's go to figure 6. Figure 6. So figure 6, figure 5 look really similar. So let's actually pull these next to each other and see what we can learn from comparing them. Okay. Figure 5 versus figure 6. So what we're seeing in the difference here is, looks like it's this item 32 here that's wrapping. All right, so figure 6, illustrating the effect of shielding on the radial magnetic field induced on a planar circular conductor by a coplanar coil. Okay, so we're going back to talking about that shielding that we saw, which I believe that's in figure 3B. This is the shielding that's occurring right here. So that's what we're referring to, just a different angle for it. Figure 7. Getting a little more complicated here. And you can start to see that aspects of figure 6 are basically being applied to figure 7. Figure 7 seems to be a larger version. Figure 7 is illustrating a basic embodiment of the present invention using a circular thrust assembly to produce an axial thrust. Okay. So we have, it looks like multiple of figure 6 combined to produce figure 7. Let's go to figure 8. This illustrates the use of the Helmholtz coils for the magnetic field enhancement. So we're enhancing figure 7, I believe. And figure 9. Okay, so we're going to rotate the diagram we were just looking at, illustrating one embodiment of the present invention using circular thrust assembly to produce an in-plane lateral thrust. So producing, looks like thrust in the upwards direction here. Okay, figure 10. Figure 10 is going to be the best mode of the present invention, using the circular thrust assembly, producing axial and lateral thrust. Figure 11, a plot of theoretical calculations versus data, experimentally illustrating the shield effect on the axial magnetic field. Okay. Let's scroll down to the detail description. So the basic invention is figure 7. Okay. Let's go to figure 7. We have figure 7. presents a top view of the geometry of the invention, as well as a method of generating force and moments. Circular conducting coil, item 14. So coil consisting of one or more turns of insulated conductive wire carrying a current, which is number 7. 7, current, covered on 3 separate segments with shielding. So shielding material is 16. Shielding material. Coil and shields form a reaction thrust assembly 64. So 64 is the combination of 14 and 16. Attached to a support plate. So 20, support plate. Threw that off for a second. Okay. 20 is a support plate. An energy supply unit. So 77. Energy supply. Okay. Attached to the plate and has a conductive wire 78 supplying the current. Okay. So the current coming from the center 77 through 78 out to the wire. When we energize with varied currents, field activation coils produce magnetic fields. So that's normal. These are the magnetic fields that I'm circling, 28 to 23. 23 has a reverse polarity for the purpose of the illustration, which fields interact with current 7 in the unshielded segments of coil 14 on the reaction thrust assembly, producing a unidirectional Lorentz force. Okay. The result is a net unidirectional Lorentz force comprising the vector sum of the 3 forces. Forces 43, 48, and 4. So these will make this yellow, greenish yellow. So these are the forces. And I think in this case, they're kind of coming out of the page at us. Okay. We can enhance this with figure 8, top-down view. Let's pull up figure 8 again. So now we're looking at a similar view with a little bit less detail, but we're focusing on other parts of it. Still, we have 14, the coil. Let's go back to red. Coil. One or more turns of insulated conducting wire. Shielding material, same stuff as we saw on the previous. Structurally supported by plate 20. Specific geometries. Having reverse polarity with respect to fields 2 and 3. Vertically summed to produce a Lorentz force. Okay, so what is the difference really between figure 7 and figure 8? Let's take a look. Side by side. Figure 7, figure 8. Figure 7 and figure 8. Okay. Just seems like it's a more detailed version. I'm not entirely sure where the difference is. We'll have to dig into that at a later time. Okay. Present mode of the invention, or the best mode of the invention, viewed in 10, figure 10. Let's get that. Okay. That's figure 9, figure 10. So we're seeing that this is pretty much that sideways view of what we saw top down before. I'm curious, I think 15 is going to be that unidirectional force. So let's see. 6 field activation coils. Okay, so these are field activation coils having magnetic permeability cores positioned symmetrically. One of each pair radially inside and one radially outside. I get it. Okay. 15, 15, 15, 15, 15, 15. It creates 6 field activation coils. Okay. So pretty much going into further detail about this part of it. An engineering analysis code was developed to design and predict the performance of this. Figure 11 illustrates the accuracy of the engineering design model in predicting the radial variation of axial magnetic field strength for both shielded and unshielded fields perpendicular to the axis of symmetry of a neodymium cobalt disk magnet. This model is then used to design and calculate the performance of the two configurations we saw, figure 7. One design operating a current of 1 amp and the other operating at 2 amps. Diameter of the reaction thrust assembly in both configs was 12 inches. Both designed to operate nominally at 100 watts of power. Here's a breakdown of the power outage or output. I'm not really in a position to understand what this means yet. That's all right. So how do we, let's just wrap this up here, kind of going through the figures. And once again, this is super high level, just trying to bring awareness to these topics. For 2 amp configuration, we got some details. The field activation coil is comprised of 500 turns. Okay, so this is actually important. The engineering design specific calculations. For a 2 amp config, the reaction thrust assembly coil is comprised of 500 turns of 0.0403 diameter, 18 gauge copper wire, having a linear resistance of 6.385 ohms per 1,000 feet. Field activation coil is comprised of 5,000 turns of 0.0403 diameter, 18 gauge copper wire, wound onto a 2-inch diameter metal core having a magnetic permeability of 2. This wound coil has 20 turns axially, 25 turns radially. 6 field activation coils. So that's the 15s, the 15s that we're looking at here, the 6 of those. Evenly spaced, 60-degree intervals. Magnetic field shield assemblies comprised of 3 layers of mu metal magnetic shielding with 50% measured field reduction for each layer. This produces a total shielding effectiveness of 87.5%. So these 2 amp currents applied to all conductors. Each field activation coil produced 1.006 newtons of thrust for a combined system thrust of 6 newtons at 100 watts. Calculated system power consumption was 16.56 watts. These design values are also produced in Table 1 for comparison with experimental results of several propellantless propulsion devices. So thrust is pretty high compared to, well, we'd have to, yeah, so if you look at the actual kilowatts per newtons, it's 0.017, Byfield-Brown at 0.7. NASA has M drive 186, NASA's M drive 2015, 1,000. So it seems to be a lot higher. Seems like this needs some refinement potentially. All right, and we'll wrap this up here with the obvious considerations. So certain claims are not presented in detail here. And for use, for example, the use of stepper motors to vary field activation coils, orientation angles. So these are things that are not in the patent, but could be of value to engineering this. The use of 2 concentric reaction thrust assemblies of different diameters to bracket 1 circumferentially array. The use of 2 concentric reaction thrust assemblies of different diameters to bracket 1 circumferential array of field activation coils. Enclosing parts of the field activation coils in magnetic field shields. The use of exotic magnetic field shielding materials, potentially metamaterials. Variations of the present invention. These will become obvious to spacecraft propulsion design experts based on mission requirements. Understood, of course, numerous characteristics and advantages of the present invention have been set forth, together with details of the structure and function of the invention. This is an illustrative disclosure only, and changes may be made in detail, especially in matters of shape, size, arrangement of parts, etc. So this is just once again, way of potentially engineering this kind of stuff. But there's other variations as well. We're going to be looking at those down the line too. So with that, we'll go ahead and conclude this video here. We have one other patent from James Purvis to go through, which I'll be releasing later this week. And then there's going to be some other papers as well that I'm going to be going through. So thank you.